All right, this is Precalculus, chapter 14, lesson 2 on page 918. We're going to look at the limit of a constant and the limit of the identity function. Okay, right here is my f of x. Here is my f of x. So this one says f of x is 7. That's why it's called the limit of a constant. The equation is a constant. This is the identity. That's y equals x. Okay, we're going to graph them. Got it? Right here in this space is not the limit. The limit goes right here. We're going to determine what the limit is. 2 is my c in both of them. So we're asking in both of them, as x approaches 2, what is the limit of that function? Okay, all right. What does f of x equals 7 look like? It's a horizontal line at 7. So here's 7. Here's 2. We'll just say that. Okay. What does this look like?
No, it's like a 1 over 1 line, if that makes sense.
It's the identity. As x is 1, y is 1. When x is 2, y is 2.
Yeah.
Got it? When x is 3, y is 3. It's called the identity function. Why do you think it's called the identity function? Because they're identical. X and y are identical numbers. It's called the identity function. Because when x is 1, y is 1. When x is 2, y is 2. Got it? Okay. All right, so those are the functions. All right, now, what is this asking us? Let's look at the constant function. This is the constant function, all right? As x approaches 2, what is y approaching? 7. So what's the limit? 7. That is true of all constant functions. Here's the formula. The limit as x approaches a number of any constant is always going to equal that constant. The limit as x approaches any number of a constant function will always equal the constant. All right, so what is the limit as x approaches negative 2 of 8? It's 8. Got it? Why? Because what does this look like? Looks like a horizontal line at 8. If I graph this, it would be here. Here's negative 2. From the left and the right, what is y approaching? So you can always know the limit of any constant is the constant. I don't care what number it's approaching. Right? So the limit of 5 as x approaches 100 is what?
5.
It's 5. Got it? Okay. The limit of a constant, regardless of what it's approaching, is the constant. That's a rule. That is a property of limits. The limit of a constant is the constant. All right? Now, let's look at this one. Here's the function, right? This is asking the limit of x. This is your function, right? As x approaches 2. All right, so as x approaches 2, what is y approaching?
2. So, will it equal C?
Yes, this will always equal c. The limit of the identity function will always be your C value. So the limit of x as x approaches C is going to be C. So the limit of x as x approaches -5 is what? -5. That is correct. The limit of x as x approaches 100 is 100. Got it? Two properties. A constant is a constant. The identity is the C value. All right. Now look on page 919. Here are some other properties. The limit of two functions added are the individual limits. Okay. So let me just make a couple up. We'll just make a constant limit. And we'll make an identity limit. All right. So the limit of 8 as x approaches 2. What is that? Okay. And then the limit, and we'll call this f of x. We'll call this g of x. Okay. Of x as x approaches 2 is what? 2. Okay. So we could say the limit as x approaches 2 of f plus g of x is the same thing as the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. All right, this limit is 8. This limit is, so it's 8 plus 2 or 10. You see that? The limit of functions added is the same as the individual limits added. I gave you the simplest functions, all right? The limit of them subtracted is just them subtracted. So the limit as x approaches 2 of f minus g of x is the same thing as the limit as x approaches 2 of f of x minus the limit as x approaches 2 of g of x, which would be 8 minus 2, which is 6. Does that make sense so far? We're going to use this with functions. Things like 2x plus 3. So I'll show you this one in a minute. All right. Now, the next one is the limit multiplied is the same thing as the individual limits multiplied. So as x approaches 2 of f times g of x, it's the same thing. I wrote it kind of close. It's the same thing as the limit as x approaches 2 of f of x times the limit as x approaches 2 of g of x. So this would be 8 times 2, which is 16. Got it? We're going to do one more. Division. So the limit as x approaches 2 of f over g of x. Now in this one, something has to be true. The limit of g of x cannot be 0. because this is the limit as x approaches 2 of f of x divided by the limit as x approaches 2 of g of x. So this limit in the denominator cannot be 0. So that's 8 over 2, which is 4. Okay, we're not going to do this. We're going to do example 1. It's harder. Okay, but we're going to use these properties and these concepts, these two concepts, to find the limits of these polynomial functions. Look at example 1. All right, we want to find the limit as x approaches -4 of that function. I'm going to write the function here of x squared minus 2x plus 3. Well, this is the same thing as the limit as x approaches -4 of x times the limit as x approaches -4 of x. See how I got that? That's x squared, isn't it? Didn't we say that was a property? Mm-hmm. Okay. Now we're subtracting, right? I'll put these in together. Now we're subtracting. And y'all can probably follow me at the top. All right. Now we're going to do 2x. That's the limit as x approaches -4 of 2 times the limit as x approaches -4 of x. That's that 2x, right? Then we'll do the 3 plus, this is by itself, the limit as x approaches -4 of 3. Then I'm going to show you a much easier way. I mean, so easy. All right, what's the limit of the identity function? It's the constant. All right, so this is -4 times -4 minus. What's this limit? 2 times -4 plus, what's this limit? 3. All right, so that's positive 16. This is going to be plus 8 plus 3. That's 11 and 16, which is, it's what? 27. So what's the limit? 27. That's my limit.
So you're not plugging in all of the decimal numbers? Like we used to plug in, like we're not doing -4.00.
Correct. Okay. Now let's go back to the original. Is -4 defined for this function? Is the value where x is -4, do we have an output for it? We do. How do you know? Because this is my domain, right? X is my domain, and my limit is the range. Okay. What is the domain and range for this function? Well, what is the range for this function? Potential could be all reals, right? Except it's really the vertex up. All right, so as long as -4 is at the vertex, or actually it's all reals for x, but the domain, the range would be wherever the vertex up is. So every value of x would be defined here because the range, the domain for this function is all reals. When would the domain not be all reals?
When it's like a sideways function. So it's,
When it's a what?
when it's y squared.
When it's not a polynomial. When do we not have a polynomial? When we have an x in the denominator, or we have an x under a radical. All polynomials domain is all reals. Okay, I could have, because I know that the domain is all reals, just plugged in -4 for x. That's actually what we did. -4 times -4 minus 2 times -4 plus 3. Did y'all catch that? The problem is, look at example 2.
So 27 is the answer.
What?
So 27 was so you're just plugging,
27 was the answer. Okay.
so you're just plugging in C for polynomials.
Always plugging in C for polynomials. That is correct. All right, look at example 2. Now we have an x in the denominator, and we're asking for the limit as x approaches 2 of x cubed minus 3x squared plus 10 over x squared minus 6x plus 1. All right, so I could ask myself, does 2 make the denominator equal to 0? So does it? That would be 4 minus 8, 12. 4 minus 12 plus 1, that's not 0. So because I know it's defined, what can I do? I can plug C in for x. I can plug this 2 in where there's an x, as long as I know that the denominator does not equal 0, and that will give me my limit. So that's 2 cubed minus 3 times 2 squared plus 10 over 2 squared minus 6 times 2 plus 1. That's 8. Let's just do it. 8 minus what? 12 plus 10 over 4 minus 12 plus 1. So that's 18 minus 12. 18 minus 12, which is 6. 5 minus 12 is -7. So my limit is -6/7. So when the range is defined, when you plug in the domain, you just can plug it in. You don't have to go through the limit of the constant is the constant, the limit of x is the C value.
So if it wasn't defined,
We're about to do it. We're about to do it. All right, you understand those so far? All right, let's look at example 3. Now it's not going to be defined. This is the limit as x approaches 3 of x squared minus 2x minus 3 over x minus 3. So it is not defined, is it? Okay. Can we factor the numerator?
yes.
Okay, so what is the numerator?
X minus 3x plus 1.
Notice what we have. We have a hole in the graph. That means there's this continuity. That means we're here, here, here. When we get to 3, there's a hole, but it keeps going. When there's a hole in the graph, we call it a removable discontinuity. Holes are removable discontinuities. Vertical asymptotes are not. Holes are where there's a 0 of the numerator, that's a 0 also of the denominator. So look what happens. We can eliminate it. It's a removable discontinuity. it's still not defined at x equals 3. There's no output that you get when you plug in 3 because you're going to get an error. But this looks the same as that because we have the removable discontinuity. So you plug 3 in, and what's the limit? 4. It has a limit when there is a removable discontinuity. It's only when you can cancel factors in both the numerator and the denominator.
I'm gonna have vertical.
Okay? All right, here's where there's not a removable discontinuity. This is not a removable discontinuity because this would be x minus 3 times x plus 1 over x minus 3 times x minus 3. Look, only one eliminates. You do not have a removable discontinuity here. This is when we have to look at 3. What happens at 2.999? What happens at 3.001? That's when we have to do this. Because there is a vertical asymptote at x equals 3. Okay? The only time you have a removable discontinuity is when there's a hole in the graph and you can cancel both factors out. Got it? Everybody got it? All right.
So are we gonna have to solve one like that?
Well, we already did some like this. In lesson 1,
Yeah.
we did some like this. We were really all of lesson 1, we did a lot of this.
Do you do it with the top and the bottom?
Yes. You plug. So what would I have had then? I'd have had x plus 1 over x minus 3, right? So I would have plugged in 2.999 in here. 2.999, 2.999. The denominator is a very small negative number, so it's going to go to negative infinity. Small denominator, big number, big output. And then I'll plug in 3.001. Small positive is going to go positive infinity as x gets bigger. All right? So it's going to be, there's no limit because it's going to go like this and something like that. Yes?
Do you have a minimum of those numbers you plug in? Like, would 2 be okay in this case? Because you see that it's going like really high or really low?
No. We want delta to be small. What is delta here? Delta is 0.001. We want delta to be small.
So like, oh, that's right. Like, is that the? I mean, like, can I plug in just 2.999 and 3.01? Like, delta is just 0.00.
As long as you then obviously see that they're going in opposite directions.
Okay.
Sometimes they're approaching the same value. You saw that in lesson 1. Like sometimes this one might give you, I'm just making this up. I don't know, 2.554, and this one might give you 2.553. So then I would say the limit is 2.55 because they're approaching the same value, right? I'm making these numbers up. All right. Now, the last example gives you a peek into, well, all of this is a peek into calculus, but the difference quotient. So the difference quotient is what we're dealing with here. In calculus, we call it the derivative. So I want you to know the difference quotient, the DQ, is the derivative in calculus. What does the derivative give us? The difference quotient gives us a new function, which is the derivative. And the derivative gives us the slope of a line that intersects a curve at one point. So, like, if this is my curve, then this would be that, the equation of that line would be my derivative. Okay? All right, so we're going to look at the difference quotient. This is where most calculus courses start out. Here's the difference quotient. It's f of x plus h minus f of x all over h. Yeah, they did give it to you. Okay. That's the difference quotient. That's the formula for the derivative. All right, so now look at example 4. It tells us that f of x is x squared. And it wants us to find the limit as h approaches 0 of f of 5 plus h minus f of 5 over h. Well, is this function defined where h equals 0? No, it's not. All right, but I'm going to do this with this function. What does this tell me to do? Plug in 5 plus h where x is. All right, so this piece right here is going to be 5 plus h squared. Right, this is my x value. I'm squaring it. Now this says just subtract f of 5. This says now plug 5 in where x is. So that's 5 squared. That's correct. All over h.
And that's the limit.
Well, we're not done. Okay, we got to do the algebra. All right, 5 plus h squared.
25 plus 10h.
25 plus 5h and another 5h. This is 5 plus h times 5 plus h, right? That's 25 plus 5h and another 5h. So plus 10h plus h squared minus 25 all over h. Our 25s cancel out. So we're left with the limit as h approaches 0 of 10h plus h squared all over h. Factor out an h, and h can be canceled out of every term. So it's the limit as h approaches 0 of what? Of 10 plus h. What's the limit as h approaches 0 of 10 plus h? It's 10 because h is 0. So what did we do? This is why we use the derivative. This is why we use the difference quotient, because you eliminate the value that makes it discontinuous. You're always going to eliminate the value in the denominator that makes this undefined by using the difference quotient.